prepare yourselves for an extraordinary cosmic event of immense proportions. Betelgeuse, the colossal red giant star perched on the edge of our galaxy, is emitting unsettling signals across the cosmos. Utilizing the James Webb Space Telescope, astronomers have made a profoundly disturbing discovery regarding this massive celestial entity. With esteemed astrophysicist Brian Cox issuing a solemn warning, the looming question arises: are we on the brink of witnessing a cataclysmic supernova explosion that could forever alter the familiar night sky? Let's delve into the details. In the vast expanse of the universe, where stars come into existence, live out their fiery lives, and eventually perish in spectacular displays, one star has recently captured the attention and concern of scientists and the public alike. This star is Betelgeuse, a red supergiant of immense size and age prominently situated in the Orion constellation. Its distinctive red hue and variable brightness have long intrigued observers, but recent developments have intensified interest in this cosmic giant. As we examine the nature of Betelgeuse, we find ourselves on the verge of a potentially monumental event in the star's life cycle. Betelgeuse, approximately 764 times larger than our Sun, is truly a stellar behemoth. Its staggering size is almost beyond human comprehension. Imagine a star so immense that if it were to take the place of our Sun, its surface would extend beyond the orbit of Mars, engulfing Mercury, Venus, Earth, and Mars itself in its fiery embrace. This immense size not only speaks to Betelgeuse's physical characteristics but also indicates its stage in the stellar life cycle. As a red supergiant, Betelgeuse is in the twilight of its existence, a phase marked by expansion and cooling following eons of fusing hydrogen into helium in its core. But what about Betelgeuse's age? This star, estimated to be around 8 to 85 million years old, may seem young in human terms but is ancient in the context of stellar lifetimes. Its current red supergiant phase represents the culmination of millions of years of stellar evolution, a period marked by dramatic changes and processes that have transformed it from a hot blue star into the red giant we see today. The life cycle of stars like Betelgeuse is a saga of transformation driven by the relentless forces of nuclear fusion and gravity. Betelgeuse's distinctive red color is another hallmark of its current stage, a result of its relatively cooler surface temperature compared to stars like our Sun. But Betelgeuse's enigmatic behavior doesn't stop there. Its variable brightness adds another layer of intrigue. Betelgeuse is a semi-regular variable star, its luminosity waxing and waning in a characteristic dance that has fascinated astronomers for centuries. However, what truly sets Betelgeuse apart is its irregularity. Unlike many stars that follow predictable patterns, Betelgeuse occasionally deviates from its rhythmic cycle, hinting at complex and less understood processes within its colossal form. In a recent groundbreaking development, Betelgeuse startled astronomers and stargazers worldwide with an unexpected and dramatic change in its appearance, now famously dubbed the Great Dimming. In late 2019, this bright star began to mysteriously dim, losing its luminosity at a notable rate until it reached its lowest brightness in February 2020. Betelgeuse, typically visible to the naked eye even in light-polluted areas, became noticeably fainter, a phenomenon that even amateur observers could discern. One challenge in monitoring Betelgeuse's activities is the time paradox. When we observe a star like Betelgeuse, we're not seeing it as it exists in the present but rather as it appeared in the past due to the time it takes for light to travel to us. Approximately 725 light-years away, the light we perceive from Betelgeuse today actually left the star nearly 7 centuries ago. This time delay makes it difficult to predict and monitor sudden changes in a star's behavior, as we are essentially looking into its past. The recent dimming event of Betelgeuse highlighted the inherent difficulties in real-time astronomical observations and the challenges posed by the vast cosmic scales and the time paradox they introduce. Andrea Dupree, Associate Director of the Center for Astrophysics at Harvard and Smithsonian, and her team closely monitored the unfolding events. They utilized the Hubble Space Telescope to analyze the massive star as part of a 3-year study aimed at monitoring variations in its outer atmosphere. These observations provided valuable insights into the dynamics of a variable star like Betelgeuse, which experiences regular expansions and contractions leading to fluctuations in brightness. Hubble's sensitivity to ultraviolet light allowed researchers to investigate the layers above Betelgeuse's surface, heated in part by the star's turbulent convection cells. By analyzing Hubble spectra taken throughout 2019 and 2020, scientists were able to measure the movement of material in Betelgeuse's outer atmosphere. Specifically, they focused on magnesium Roman II lines, which provide indications of atmospheric conditions. These observations revealed material moving at speeds of about 200,000 miles per hour from the star's surface into its outer atmosphere. This hot, dense material eventually extended millions of miles from Betelgeuse and preceded the formation of the dust cloud responsible for the star's dimming. Dupree and her team estimated that roughly twice the normal amount of material from Betelgeuse's southern hemisphere was lost over the 3 months of the outburst, a significant mass loss considering that all stars, including Betelgeuse, continuously shed mass, although at a rate much higher than our Sun. The scale of this mass ejection and the subsequent dimming led to discussions among astronomers about whether it could be a precursor to a supernova explosion. Betelgeuse's relatively close proximity to Earth, about 725 light-years away, adds to the intrigue, as any such explosion would be visible from our planet, providing a rare opportunity to observe a supernova up close. However, the question remains, what does this dimming event signify for Betelgeuse's future? Is it an indication of an impending supernova, or simply a unique episode in a star's lengthy and complex life? Various theories were proposed to explain this sudden change. One prevalent theory suggested a phase in the supernova explosion process, gaining traction due to the common belief that Betelgeuse is nearing the end of its life. Another theory implicated dust, possibly originating from the star itself, obscuring our view. Betelgeuse, like other red supergiants, is known to shed material, which could form a dust cloud dense enough to dim the star's light from our perspective. A third explanation considered changes in the star's photosphere, the visible surface layer, which could affect its apparent brightness. In-depth analysis using various observational methods helped unravel this mystery. Spectroscopic studies indicated a drop in Betelgeuse's effective temperature, suggesting that the dimming could be due to a large dark spot on the star's surface. This theory was supported by observations showing that Betelgeuse's temperature dropped by at least 170 Kelvin around the time of the dimming, indicating significant changes on its surface. Ultimately, the key to understanding this unusual phenomenon came from humanity's eye in space, the Hubble Space Telescope. Hubble's observations revealed that Betelgeuse's dimming was likely caused by a significant ejection of hot material into space, forming a dust cloud that obscured a portion of the star's surface and reduced the amount of light reaching us. This dust cloud was believed to have formed from superhot plasma erupting from a large convection cell on the star's surface and then moving through its atmosphere to the colder outer layers, where it cooled and formed dust grains, creating the observed cloud. Hubble's ultraviolet light spectroscopic observations, initiated in January 2019, played a crucial role in piecing together the timeline leading up to Betelgeuse's darkening, capturing signs of dense, heated material moving through the star's atmosphere in the months preceding the dimming. In December 2019, several ground-based telescopes observed Betelgeuse diminishing in brightness, particularly in its southern hemisphere. The material emitted initially brighter than the star's usual luminosity eventually coalesced into a dark cloud as it dispersed outward and cooled. This outflowing material and the resulting dark cloud were hypothesized to be the cause of the star's sudden dimming. The magnitude of this ejection was monumental, thrusting Betelgeuse into the astronomical spotlight. The star expelled an estimated 400 million times the mass typically released in a standard coronal mass ejection. This mass, believed to weigh several times as much as our Moon, marked a significant event not only for Betelgeuse but also for our comprehension of stellar mechanics. This immense ejection of material holds profound implications for supernova theories. Traditional understanding suggests that red supergiants like Betelgeuse steadily shed mass before their explosive demise. However, the scale of this ejection challenges this notion, indicating a potentially turbulent and unpredictable final phase for these stars. Could Betelgeuse be preparing for its grand finale, a supernova explosion in the coming millennia? Recent studies speculate about the timing of such an event, proposing that it could occur sooner than previously believed, possibly within a few tens of years. Another crucial aspect of the Betelgeuse puzzle is the concept of the bow shock. As the colossal star travels through space at around 67,000 miles per hour relative to its surrounding interstellar medium, it generates a bow shock akin to the wave formed by the bow of a moving ship. This phenomenon occurs as the star's outer layers interact with interstellar gases and dust, showcasing the star's dynamic nature and its interaction with the cosmic environment. Studying this bow shock informs us not only about Betelgeuse's current state, but also contributes to our understanding of stellar evolution and mass loss processes. Regarding Betelgeuse's recent behavior, observations indicate that its surface has cooled and become less dense following the mass ejection event, leaving the star in an unstable state even years later. Hydrodynamic simulations suggest a link between the star's convective activities, mass ejection, and subsequent pulsation mode switching. This ongoing instability raises questions about the internal processes driving these changes and their potential outcomes. Moreover, Betelgeuse's observed mass loss rate is significantly higher than that of many other stars, suggesting a complex interplay of internal forces. With all these dramatic changes, the question of whether Betelgeuse is on the verge of going supernova looms large in the astronomical community. Although the timing of such an event remains uncertain, the recent unprecedented mass ejection has undoubtedly shifted the discourse, hinting at a more imminent end than previously anticipated. Theories now grapple with the ramifications of such massive material loss and its implications for the star's stability and future. Meanwhile, amidst the scrutiny of Betelgeuse, another cosmic event seizes our attention: the supernova SN 2023X. This spectacular explosion occurred in the Pinwheel Galaxy, just 21 million light-years away, making it the nearest supernova observed in recent years. Its discovery by amateur astronomer Koichi Igaki and subsequent study provided invaluable insights into the nature of stellar explosions and their surrounding environments. Spectral analysis revealed a dense shell of gas surrounding SN 2023X, influencing the behavior of the supernova shockwave and prompting further investigation into the star's pre-explosion conditions. In either case, it's estimated that Betelgeuse lost up to a solar mass of material in the last 1 to 2 years of its life, indicating that its final moments were anything but serene. Identifying the progenitor of SN 2023X has become a focal point of study, with researchers converging on a likely candidate: a red supergiant. By studying the details of SN 2023X's explosion, including its progenitor's characteristics and the mechanisms leading up to its final detonation, astronomers can refine their models of stellar evolution and supernova mechanics. These insights directly inform our understanding of Betelgeuse's current state and its potential path to supernova, offering a clearer picture of what signs to look for and how to interpret the massive red giant's complex behaviors. But when will Betelgeuse explode into a supernova? Research from Japan's Tohoku University suggests that Betelgeuse might currently be in the carbon-burning stage of its life, a phase typically preceding the end of a star's life. Hawkey, the leader of this study, posits that the star's core could collapse a few tens of years after the carbon is exhausted. Conversely, researchers from Hungary's Connolly Observatory believe Betelgeuse is in an earlier helium-burning stage. Despite these different views, there is a consensus that Betelgeuse is likely to be the next supernova in the Milky Way, although this event might not happen for another 100,000 years. Historically, observations of supernovae have provided invaluable insights into stellar deaths. The earliest confirmed record of a supernova, dating back to 185 CE, was observed as a bright star that took about 8 months to fade from the sky. Since then, several significant supernovae have been recorded, including SN 1006, the brightest recorded star ever to appear in our night sky, visible across various parts of the world, and SN 1054, which resulted in the formation of the Crab Nebula and was visible in daylight for 23 days. The most recent supernova observed in the Milky Way was SN 1604, studied extensively by Johannes Kepler. More recently, supernova 1987A in the Large Magellanic Cloud was observed within hours of its light reaching Earth, marking the first supernova detected through neutrino emission and observed across every band of the electromagnetic spectrum. These observations have been crucial in developing successful models of supernova behavior and understanding their role in star formation. Observing supernovae has been a transformative endeavor in the field of astronomy, providing not only insights into the death throes of stars, but also unveiling the mysteries of the universe's evolution. Supernovae serve as cosmic laboratories, where extreme conditions give rise to exotic phenomena and fundamental processes that shape the cosmos. By studying these stellar explosions across different wavelengths, from gamma rays to radio waves, astronomers gain a comprehensive understanding of the physics underlying these cataclysmic events. Supernovae are classified into various types based on their spectral characteristics and the mechanisms driving their explosions. Type Ia supernovae, for instance, result from the thermonuclear explosion of a white dwarf in a binary system, while core-collapse supernovae, such as Type II and Type Ib/C, occur when massive stars reach the end of their evolutionary path and undergo gravitational collapse followed by a violent explosion. Each type of supernova offers unique insights into stellar evolution, nucleosynthesis, and the dynamics of the interstellar medium. Type Ia supernovae, often referred to as standard candles, have played a crucial role in measuring cosmic distances and elucidating the expansion history of the universe. By comparing the observed brightness of Type Ia supernovae with their intrinsic luminosity, astronomers can infer the distances to their host galaxies and trace the cosmic expansion rate over cosmic time, leading to the discovery of dark energy and the accelerated expansion of the universe. Core-collapse supernovae, on the other hand, are stellar furnaces that synthesize heavy elements, including iron, nickel, and beyond, through nucleosynthesis processes occurring during the explosion. These elements are then dispersed into the surrounding interstellar medium, enriching it with the building blocks of future generations of stars, planets, and even life. Core-collapse supernovae also serve as cosmic particle accelerators, generating high-energy cosmic rays that permeate the universe and influence its evolution. In addition to their scientific significance, supernovae hold cultural and historical importance, inspiring awe and curiosity across civilizations and epochs. Ancient records from civilizations such as the Chinese, Babylonians, and Maya document the appearance of guest stars or new stars in the night sky, likely supernova explosions visible to the naked eye. These celestial events were often interpreted as omens or portents, shaping beliefs and influencing the course of human history. Today, supernovae continue to captivate the imagination of scientists and the public alike, driving research efforts to unravel their mysteries and understand their role in shaping the cosmos. Advanced telescopes and observatories, both ground-based and space-based, enable astronomers to study supernovae in unprecedented detail across the electromagnetic spectrum, from their initial outburst to their aftermath. The study of supernovae extends beyond individual events to encompass their broader impact on galactic and cosmic scales. Supernova remnants, the expanding shells of gas and dust ejected during the explosion, serve as cosmic laboratories for studying the dynamics of interstellar matter, the formation of cosmic rays, and the process of stellar feedback, whereby supernovae regulate star formation and galactic evolution. Moreover, supernovae are integral to our understanding of cosmological phenomena, such as galaxy formation, cosmic chemical enrichment, and the cosmic web, the intricate network of filaments that connect galaxies across the universe. By tracing the distribution of supernovae in space and time, astronomers can reconstruct the cosmic history of structure formation and elucidate the underlying mechanisms driving the evolution of the cosmos. In conclusion, supernovae represent cosmic milestones in the life cycle of stars, marking the culmination of stellar evolution and the birth of new cosmic phenomena. From their spectacular explosions to their far-reaching consequences, supernovae shape the fabric of the universe and provide valuable insights into its origins, evolution, and ultimate fate. As we continue to explore the cosmos and unravel its mysteries, supernovae remain beacons of discovery, illuminating the pathways to a deeper understanding of the cosmos and our place within it.